Organic chemistry is largely the study of molecules. If you want to understand anything about biochemistry, anything about medicinal chemistry, anything about organic chemistry at all, we have to understand molecules. To understand molecules, we need to understand bonding. So that's what we're focusing on today. So our first questions of the class. Video number 1. Here we go. What is a bond? Specifically, what is a covalent bond? That's the kind of bonds that we care the most about in this class. Again, bonding is what makes molecules. Bonding is what gives molecules their activities, their usefulness, their structure, everything. So we need to understand the bond before we can understand anything else. And to understand a bond, we really want to know where the electrons are in that bond. Right? That's going to tell us a lot about the molecule. And all this is building to how can we predict geometries and bond strengths in molecules just by looking at the bonds that it has. And from geometries and bond strengths, can we then go into understanding reactivity, understanding purpose, raison d'etre, if you will. But we'll save that for another day. Today we'll talk about the simplest covalent bond there is. But first, we need to talk about the simplest atom there is. Here we have a hydrogen atom, which is to say a proton, with an electron around it. Where is that electron? If you remember talking about orbitals in earlier chemistry classes, you maybe know this already, but the electron in hydrogen is in what we call a 1s orbital. What does that mean? Simply what it means is that we can think about the electron spread out in kind of, not a circle, not a perfectly Niels Bohr-ish orbit, but really as smeared out over a sphere. Right? So if I take a look at the radius versus the electron density, I would see it maximum at the middle and then drop off. Okay? So again, the electron in a hydrogen atom is most likely to essentially be at the nucleus. Okay? And then it drops off with distance. Okay, so that's a hydrogen atom. Sometimes molecules are made of 2 hydrogen atoms. So here's our second one. Okay, so now I'm going to introduce some new notation. Imagine I have this y-axis, that is energy. And I have some energy levels here. This is where my electron sits. So this is the potential energy of a hydrogen electron. So hydrogen atom in space, intergalactic, planetary, nothing around it for astro miles, right? It's by itself. This is the energy that it's at. What happens when 2 hydrogen atoms get close together? When they get close together, the orbitals, which is what these sort of smeared out electrons are, it's an orbital, the orbitals overlap. When orbitals overlap, they mix. Once more, when orbitals overlap, they mix. And what does that mixing mean? When we take 2 atomic orbitals and mix them together, we get 2 molecular orbitals. So again, I'm bringing in these atomic orbitals. They're very distant in space. One's coming from this direction, one's way out here. As they get closer together, these electron waves overlap. And when orbitals overlap, they mix. What does that mixing mean? Well, from 2 atomic orbitals, we then get 2 molecular orbitals that are just more or less combinations of the atomic orbitals that they come from. One gets lower in energy. That's when the 2 orbitals more or less just kind of merge together, right? They interact constructively. So an orbital looks like this. Obviously, if you want a better picture than this, look anywhere. I mean anywhere. Any book, the internet, chalk circles, anywhere in the world will you find a better picture of this orbital. Anyways, when you take these 2 together, you'll get a molecular orbital where the maximum electron density is between the atoms, probably right between the atoms in this case. So this is called a molecular orbital, and it's called a sigma orbital. Sigma being the Greek version of S, so from S we get sigma. Okay? This is a sigma orbital. Now, we also create something where now they're kind of fighting each other. They're not mixing in phase. And now there's no electrons in between. And so the electron density on the left side and the right side is actually kind of repelling each other. So what does that mean? We call this a sigma star, right? We call that a star. Sigma star. This lower one, this sigma orbital, is a bonding orbital. This sigma star is an anti-bonding orbital. Okay, so this is kind of some deep stuff. So let's sit back and unpack it a little bit. Again, the electrons in the sigma orbital are kind of spread out all over, but more or less mostly between the two atoms. What does this color mean? Does that mean that it's positive and negative? No. Does it mean that it's the electrons over here, but there's no electrons over there, or vice versa? No. All the different colors in your book or on the board mean is that they can't mix. We can just leave it there. They can't mix. There is a plane between them where there is 0 electron density. Electrons will never be there. And these things that can't mix actually repel each other. So this is quite literally an anti-bonding orbital. Okay, how should we use this? What does it mean? Is it real? Okay, well, let's back up again. I've got 1 electron coming from each of these atomic orbitals. So in my 2 molecular orbitals, I can put 2 electrons in. And don't worry about this spin I've shown here, right? Electron on its own, we don't care. As I fill my molecular orbitals up, both electrons can fit in this bonding orbital. And I don't have any electrons in this anti-bonding orbital. Does that mean the anti-bonding orbital isn't real? Well, what even is real? Just think about that for a second. What is real? Makes you think. In our case, we can kind of think about it like, well, if I was to shove another electron in this system, right? So if I have my little hydrogen molecule and I am by great force kind of forcing another electron into the system, that electron is going to go here and be spread out on the periphery and not in the middle. So that's where that extra electron would be. It also tells me that if I take this electron and give it this much energy so I can kind of punch it up here, once again, I can ask, where is that electron? And the answer is, it's on the edges, it's not in the middle. So I have 2 electrons holding it together, 0 electrons pushing it apart. Another way to think about that is I had 2 electrons get lower in energy. So this is a stabilizing force. All right? Again, when things get lower in energy, they get more stable, right? Just like a marble rolling down the hill is giving up potential energy. Here, I'm giving up potential energy to go down here. If I were to try to rip apart this bond to break this HH bond, that would be endothermic because I would need to take these electrons and get this much more energy in them to pop. Sometimes we call that the Morse potential, where I say how long can my bond length R get and what does the energy look like? Well, the energy has some minimum here. If they get too close, they get really unhappy. If they get too far away, they get kind of unhappy, and then they're just broken. And here, if they're broken, they're broken. They're just two atoms by themselves. So again, this bonding is a stabilizing process, right? We are gaining this much energy in stability, right? We're rolling downhill. If I want to break a bond, I need to put energy into the system to get back up from here to there. In the next video, we're going to look at a molecule that's even more exciting than H2, which is every molecule. H2 is the worst molecule. It's boring, but now we understand the sigma and sigma star orbitals.